A massive eruption tears away from the sun and races into space. Not a flare fading into the background, but a fast-moving cloud of solar material headed straight through the inner solar system. At first glance, it seems like the kind of event Earth should be protected from. Something that would be tracked, predicted, maybe even defended against. Then, scientists looked closer. The storm kept moving, and a NASA spacecraft called Stereo A measured it directly after it left the sun. Years later, researchers replayed the event and noticed something unsettling. The eruption crossed the exact region of space where Earth had been only about a week earlier. Picture a doorway swinging shut just after someone steps through it. The storm arrives seconds too late. In visualizations of Earth's orbit, it looks even worse. A bullet passing through an empty doorway after the target has already moved on. Nothing stopped it. No shield intercepted it. No emergency system pushed it away. Earth was simply gone when it arrived. And that changed the meaning of survival. Safety no longer looked like preparation. It looked like timing. And timing can run out. Researchers began comparing the July storm to the most extreme solar events ever recorded. As the measurements came in, the comforting explanation started to fall apart. This was not looking like routine space weather anymore. The numbers pointed towards something far closer to the upper edge of what had been seen before. And that changed the threat. The danger was no longer confined to a handful of satellites orbiting overhead. It started spreading through the systems connected to them. Modern satellite infrastructure sits quietly above daily life, but its signals reach far beyond navigation. GPS timing helps synchronize systems that most people never associate with space. Communications networks depend on it. Banking systems rely on precise timestamps. Logistics networks coordinate around it. Electrical grids use timing signals to stay aligned. On a world map, the connections seem to multiply. Lines spread across continents. Communications, banking timestamps, logistics networks, and electrical grids all light up together, linked by invisible timing signals moving through space. The fact itself is simple. Modern civilization runs through interconnected systems that depend on stable space weather. The consequence is harder to ignore. A single storm no longer has one target. It suddenly gains multiple paths into the same civilization at the same time. And all of those paths lead back to the same source. But there is another reason the July event can seem less frightening than it was. Today, the sun is not being watched blindly. Solar observatories continuously track activity across its surface. Satellites watch eruptions as they break away and move outward. Inside space weather forecasting networks, analysts follow those disturbances in real time, measuring their speed and direction as they cross space toward Earth. Then the alerts begin moving. Forecast centers issue warnings. Control rooms receive notifications long before the disturbance arrives. Operators review forecasts, prepare procedures, and make decisions before impact. That alone marks a dramatic change from the era of historic solar storms. We are no longer waiting for the sky to surprise us. Space weather monitoring has improved enormously. Major eruptions can be detected, tracked, and followed as they travel through space. In many cases, advance warning arrives before the geomagnetic disturbance reaches Earth. And that creates a powerful sense of control. The threat is still there, but now it appears visible, measurable, manageable. The picture almost feels reassuring. We can see the storm coming. Warnings move through forecasting networks. Operators prepare. Systems have time to react. For a moment, It seems the problem was solved the moment humanity learned how to watch for it. The warning arrives. Forecast centers push alerts. Operators begin preparing for impact. Everything about that sequence suggests control. If seeing the storm is enough, then the danger should end when the storm passes. Damage might happen, but recovery should follow quickly. The problem would be prediction, not survival.
Clear on this side, keep coming.
Then the focus shifts from the sky to the ground. A massive high-voltage grid transformer creeps down a highway under escort vehicles. It is larger than a house. Traffic is cleared around it. Every turn is slow. Every bridge and roadway along the route matters. This is not equipment pulled from a warehouse shelf. Many of these transformers are custom built. They move through specialized manufacturing and transportation chains before they ever reach the grid. And that changes the meaning of the warning. The forecast can arrive early. Operators can prepare. Damage can be reduced. But the warning cannot manufacture a replacement. The belief begins to crack. Forecasting no longer looks like protection by itself. It looks like only the first step. Because recovery depends on physical hardware that cannot appear on demand. Once enough of those transformers are lost, the clock stops measuring hours. It stops measuring days. The timeline stretches outward into months and even years. The threat is no longer just whether the storm can be detected. The threat is whether the system can be rebuilt after the storm is gone. And those are two very different problems. The July 2012 eruption appears again. The same cloud of solar material tears away from the sun. The same near miss crosses Earth's orbital path. But now the event looks different. The camera pulls back. Satellites circle overhead. Power lines stretch across continents. Data centers process information every second. Logistics hubs move goods through supply chains. Timing systems quietly keep distant networks synchronized. One by one, the connections appear. Many of the systems modern life depends on are tied to infrastructure that cannot be rapidly replaced. Satellites require recovery. Transformers require manufacturing and transport. Timing systems depend on broader networks. Supply chains depend on the systems around them. The links keep multiplying until the network begins to look less like separate machines and more like a single system. And then the failure becomes obvious. Knowing a storm is coming does not create replacement hardware after the storm arrives. A disruption can happen quickly. Recovery moves at the speed of manufacturing, transportation, installation, and coordination. That is why a single solar event can become a prolonged societal problem. The disturbance moves fast. Replacement moves slowly. The July 2012 near miss was never only a story about the sun. The sun creates the disturbance. Dependency and replacement bottlenecks determine the scale of the damage. The storm wasn't the weakness. We were.